Welcome everyone to the last topic before mid, that is the discrete Fourier transform. This is actually the first topic of frequency domain analysis of signals. And before mid, we will only look at the theory of Fourier transform. We won't delve into the hows, that is how it is done. We'll just see what it does instead of how it does. And we'll delve into the mathematical details of discrete Fourier transform after the mid. And even if I do decide to cover some of the stuff after the mid, uh, before the mid, they do know that that won't be included in the mid syllabus. That is, if we do cover the mathematics of discrete Fourier transform, that won't be included in the mid exam. But that will depend on whether, how much time we have and whether it is feasible or not to cover all those things before mid. So for now, we'll start with the discrete Fourier transform. And it is actually very difficult to visualize frequency domain analysis of signals using just 2D figures and especially using pen and paper. So it is better to visualize it using some kind of computer simulation. So for that, I will also be giving links to two useful videos on YouTube from the channel 3 Blue 1 Brown. These two are the videos, and I'll be giving links to them in the Google Classroom. I recommend everyone to watch these videos before you continue with the rest of the things here. Those videos are actually very useful for understanding the basic intuition behind why we need Fourier transform and what it will actually do. What do we mean by frequency domain analysis of signals? All these things should be clear for the most part from those videos. And here we'll just go into the basic theory of it. So let us start. The Fourier analysis is basically a family of mathematical techniques all based on decomposing signals into sinusoids. And if you remember, this line actually comes from one of our previous chapters where we discussed about decomposition of signals. I think it was in chapter 5, linear systems. So there we discussed about decomposition of signals. There were various kinds of decomposition: impulse decomposition, then step decomposition, even odd decomposition, and the like. And there was also this Fourier decomposition. So Fourier decomposition is basically decomposing every signal into sinusoids. It means sines and cosine waves. Summation of various sines and cosine waves can be used to represent any arbitrary signal. So this is what Fourier analysis says. And there are actually lots of kinds of Fourier, not lots, actually four different kinds of Fourier analysis. And out of that, the discrete Fourier transform, DFT, is the one that works with digitized signals. So just by seeing this word digitized gives you the idea that there are also other versions of Fourier transform that work with continuous signals. So we'll be talking about that here later, just a few minutes now. But the thing that you have to remember is that we will only be working with discrete Fourier transform for our course. We won't be going into the continuous parts or the other versions of Fourier transform there are. Those won't be covered in our lecture. We'll only be discussing our discrete Fourier transform. We'll just know that there are some others. Okay. So another thing to ask here is that why do we consider sinusoids instead of other kinds of waves? I mean, you guys might be thinking, why do we need to represent any arbitrary signal as summations of sinusoids, sines and cosines? Why can we not just sum up different kinds of other signals like square or triangle waves? Why do we not consider them? So the reason for it is already given here. I'm just going to go through this briefly. So the basic thing is that any kind of decomposition should result in something that is easier to deal with than the original signal. So the original signal might be something very complex, like there is no way to, okay, this is continuous, this is not discrete. If it was discrete Fourier transform, then this wouldn't be like this. This should be something like this. Anyway, so this is just for visualization purposes. Okay. So the thing is that any kind of signal, arbitrary signal, should be decomposed into something that is easier to work with than the original signals. The original signal has no semblance of what it actually represents. What is the frequency? What is the actual shape? How many different kinds of signals were added to make this signal? Nothing you know about this. So after decomposing it, we should get a bunch of signals that should be elementary, that will help us to reconstruct this signal using some elementary operations like addition, convolution, and such. So the basic idea of any kind of decomposition is that we should be able to do something with the components of the signal. So square and triangular waves, the reason we do not decompose into these kinds of waves, and instead why we choose sines and cosines, is because the original signal does not have one property called sinusoidal fidelity. And this sinusoidal fidelity property, we already discussed this in one of our previous chapters. So this property is present in sines and cosines. And when we represent any signal using sum of sines and cosines, we know that each of the components will have this property, sinusoidal fidelity. So that is, and also only the amplitude and phase of the signal can change. The frequency and wave shape must remain the same. This is seen for only when we decompose every signal into sines and cosines. We see this property hold. That is, the amplitude and phase of the signal can change, but the frequency and wave shape must remain the same. And sinusoids are the only waveform that have this useful property. While square and triangular decompositions are possible, but there is no general reason for them to be useful. So that is the main reason we do not decompose into these kinds of well-known waves. So square and triangular waves are even simpler than sinusoids, right? We know that sinusoids are like this, but square and triangular waves are even simpler, right? You have seen all of this. But the reason we do not go through, we do not decompose every signal into one of these two is because they are not giving us any kind of useful insight into the various things that are given by sinusoids, sines and cosines. So that is the main reason we do not decompose into these two. Okay. Also notice that there is also another problem here. That is, sines and cosines are continuous, but square waves especially are not continuous. They are at one point, at this particular point, suppose it shifts from one amplitude to another, and then again after at another time interval it shifts. So this kinds of behavior is also problematic when you are using it for other kinds of purposes like finding the frequency and such. So this is why we avoid square and triangular waves. Instead we go for sines and cosines. Okay, and the general term Fourier transform can be broken into four categories. Like I discussed before, there are other versions of Fourier analysis rather than just DFT. But even though we will just be talking about DFT, but here we will just know what are the other forms of Fourier analysis. So, and these forms are dependent on the four basic types of signals that can be encountered. Okay. So a signal can be either continuous or discrete, and it can be either periodic or aperiodic. We all know what continuous and discrete signals differ by, and we also know how the difference of periodic and aperiodic appears. Based on that, there are four combinations: continuous periodic, continuous aperiodic, then discrete periodic, and discrete aperiodic. Based on these four combinations, we can have four kinds of Fourier analysis. The first one is aperiodic continuous. For such signals, and examples of such signals are also given here. That is the decaying exponentials and the Gaussian curve. So these are aperiodic because they do not repeat indefinitely over from minus infinity to infinity. You do not see them repeating. Also, they are continuous because there is no gap in the middle. For example, a Gaussian curve. You know what a Gaussian curve is? A bell curve, something like this. Okay, such a curve is aperiodic because this thing does not repeat from minus infinity to infinity. If you go towards minus infinity in this direction, you'll see that it gradually goes towards zero, but it never becomes zero. Also, if you go towards positive infinity, you'll see that it gradually goes towards zero, but never becomes zero. Okay, and this thing, this shape never repeats later on. Okay, it just keeps going like this, and it keeps going like this in that direction. So it is aperiodic for sure. And it is also continuous because there are no gaps in between the amplitudes. If you consider it in that way, then it is continuous. It can also be discretized. If you take the samples after a particular interval, it can be considered discrete time. But for now, we are considering the original version, that is continuous. There is no gap in between. So in that case, it is an example of so the Gaussian curve is an example of an aperiodic continuous signal. Okay, and the Fourier transform for this type of signal is simply called the Fourier transform. Okay, so the Fourier transform, this original name was used originally for aperiodic continuous signals. So, and then there is also another type of signal that is periodic and continuous. Examples are sine waves, square waves. Square waves are not exactly fully continuous because there are points of discontinuity. But in any case, we can consider that the waves do run continuously there if there are no gaps in between. The periodic continuous would be something like if you take this as one period, it repeats for infinity, right? And also continuous because there are no gaps in between. So this is an example of a periodic continuous signal. This particular period repeats indefinitely. And the Fourier analysis for this type of systems would be called Fourier series. Okay, and so this is the second term. Fourier transform was used for aperiodic continuous, and then this other term Fourier series was used for periodic continuous. Then there is another version called aperiodic discrete. For such type of signals, this is known as discrete Fourier transform. Okay, and there is also the final one, that is the one that we are going to talk about, discrete Fourier transform. This one is useful for periodic discrete. So the type of signals that we'll be considering are both periodic and discrete, because we'll be talking mainly on discrete Fourier transform, and this one works with periodic discrete signals. And actually any kind of aperiodic signal, if you take a particular portion of it and repeat it, it becomes a periodic signal, right? For example, if you think of it in this way, that a step function, or not a step function, suppose you define a signal in this way, from negative infinity to this point it is all zero, but at a particular position it starts having amplitudes, and then after a particular point it again becomes zero. So if you think of a signal in this way, and if you take this window, and then repeat it in all directions indefinitely, then this again becomes a periodic, because obviously this period repeats, and this is discrete. So such a signal can be considered as a periodic discrete signal. So initially some signal that was aperiodic, because this pattern from minus infinity to this point and from this point to infinity did not repeat. It was zero on this side and zero on that side, and in the middle there was something. So this pattern did not repeat. But if you take this window and then repeat it along both directions, then it becomes periodic and discrete signal. So every aperiodic discrete signal can be considered as periodic discrete signal if you just perform these kinds of operation on it. And usually when we talk about Fourier transform, you'll see later on, we'll see that mostly we consider things like this. We take a small chunk of it and we consider that it is periodic in all directions after that. Okay, so you'll see later on in other chapters why this thing is necessary. So now here we are talking about a finite number of samples stored in our computer, say 1024 points. A 1024 point signal is taken. So firstly, you'll notice that all four of these classes of signals that we talked about just now, so those were extended from positive infinity to negative infinity. Okay, but most of the time when we are not most of the time, all of the time when we are working with signals in a digital computer or any kind of microprocessor or microcontroller, the signals that we have are finite. Those are not infinite. So here all of these signals were periodic continuous or aperiodic discrete. All these versions were infinite. They came from minus infinity to positive infinity. So that is why just now I was talking about taking this window. So you have samples from minus infinity to infinity, but we only take some points in the middle and we consider them to be repeating from here on out. So why do we take that? Because even though there are samples from minus infinity to positive infinity, but we cannot actually store them in any kind of media. either magnetic media or optical media or any kind of media, we cannot, or we also cannot transfer them. An infinite length signal cannot be transferred over the over any kind of transmission media, either the internet or any kind of radios or anything. So you cannot think of any kind of signal when you are working with them in a finite, with finite memory. You cannot work with them if they're infinite. So that is the reason we always consider them in this way. There is, we only take a particular window, and we consider that this particular window is being repeated left or right, left and right. Okay, so this is the main point here. So suppose there are 1024 points in within this window. So this is what we're saying. So we are considering finite number of samples here, but just before, when we were talking about those 4 types of signals, those were all infinite. Those all had infinite number of samples, right? So how do we only how do we map from one to the other? So isn't there a version of the Fourier transform that uses finite length signals? The thing is, no, there isn't. All of the things that all of the Fourier transform versions that we discussed about, there is the discrete Fourier transform, then the Fourier series Fourier transform, and the discrete time Fourier transform. All of them work with are defined, not work with, they are defined on infinite points. But then how are we going to work with finite number of points? This is how we are going to work with it. We are only going to take kind of window of that. So we have a finite number of points, suppose 1024 points in a particular memory location. So the memory location will only hold data for 1024 points. But when the Fourier transform works on it, it is going to consider that these 1024 points are mathematically or virtually repeated over the positive infinity and negative infinity. But when we are storing it, we are not storing all the infinite points. We are only storing 1024 points. But Fourier transform will assume, while working, it will assume that there are 1024 points. These 1024 points are repeated on the positive direction and the negative direction as well. Okay, so this is just a heads up for now, where we won't actually understand why this happens unless we consider the mathematics of it. But for now, this is just what we need to remember, that we are storing a finite number of points, but Fourier transform is considering this to be infinite number of points. Okay, so this is the basic takeaway. Okay, so sine and cosine waves are defined as extended from negative infinity to positive infinity. And we cannot use a group of infinitely long signals. By a group of infinitely long signals, we mean the sine and cosine waves. Just like we have said, sine and cosine waves are infinite, but we are storing the signals that we are processing. For example, 1024 point signal that we are processing, this one is finite because we cannot store an infinite point signal in our memory. So we have to take a finite number of points. So we are taking a finite number of points and we are decomposing it into sines and cosines, which are infinite signals. Sines and cosines themselves are infinite. So how are we actually doing this? The way around this dilemma is to make the finite data look like an infinite length signal. So this is done by imagining. So this is just what I said just now, that we are, even though we are storing 1024 points, but when discrete Fourier transform is working on it, it is imagining it to be an infinite length signal. On the left and right, these points are repeated. Okay, if all of these imagined samples have a value of 0, the signal looks discrete and aperiodic, right? And the discrete Fourier transform applies. As an alternative, so there are actually 2 ways to make it infinite. Okay, so the one I talked about was this part, duplication of the actual 1024 points. But the other way you could have considered it to be infinite is that suppose you take 1024 points in this window. There are suppose 1024 points in this window. You can consider that to the left of it and to the right of it all are 0. There are all 0 points here and all 0 points here. You can consider this is one way. The other way is that you can consider this pattern to be repeated to the left and to the right, and this is what we mean by duplication of the actual 1024 points. In this case, the signal looks discrete and periodic. Periodic why? Because this, if you consider this to be the period, then within this all the points that are present, this will be present in all the other periods as well. In all such windows, you will see this thing repeating. Okay, with the period is of 1024 samples. And this allows the reason we consider this version of uh, infinitization, if you call this as infinitization, where we are duplicating it and making it infinite, then we this allows us to use the discrete Fourier transform. The other one does not. The other one, by the other one I mean, if you consider only this window and the rest of it all are zeros on the left and right, that does not allow us to use the discrete Fourier transform. So discrete Fourier transform imagines the signal virtually to be infinite and periodic as well. That means it repeats it. Any length signal you take, it repeats it to the left and right and performs the mathematical operations. So if you want to perform this the duplication is the one we choose. Okay, as it turns out, an infinite number of sinusoids are required to synthesize a signal that is aperiodic. Okay, if a signal is aperiodic, it would take an infinite number of sinusoids. This makes it impossible to calculate the discrete time Fourier transform in a computer algorithm. So that is why when we consider any kind of signal for discrete Fourier transform, we are talking about discrete Fourier transform. So if discrete Fourier transform needs to be applied in our algorithm, it needs to consider every signal as periodic, because otherwise it would need an infinite number of sinusoids. Okay, so this is the main reason why discrete Fourier transform considers everything as periodic. Just like I said just now, that if you take 1024 points, you have to repeat it to the left and right in order to make it periodic. Because if it wasn't periodic, if it was aperiodic, then it would need infinite number of sinusoids. That means the frequency domain analysis, in the frequency domain version of it, you would need an infinite number of spikes. Okay, so in order to make it finite, so that the frequency domain part of it also is a finite number of points, we need to consider it as periodic, not aperiodic. Okay, digital computers can only work with information that is discrete and finite in length. And why is that? I just talked about it just now. That is because the memory in digital computers are finite, even though in the real world, every information is almost like infinite. Uh, Between one point to the other, there are infinite number of points. If you consider a line, there are infinite number of points between these two, right? But this is in the physical world. But when you're storing it in the or any curve, maybe suppose you're storing a curve in the digital memory, how do you store it? In the, if you remember it from computer graphics, if you guys had computer graphics, you would know that there are actually multiple ways. One is to design a single equation for it that would generate it. The equation is finite, obviously. The memory required for storing an equation is finite, so using that equation you can generate it. Or otherwise, if you want to store up store points to generate this curve, you would need an infinite number of points. So what you do is you can perform tessellation, and you can take kind of an approximation. You just you store a finite number of points and join them using straight lines, and this is how you can approximate a curve. Okay, so that is just to remember that digital computers cannot store infinite number of points. So any kind of signal is also in the physical world is infinite, but when we are working with it in the uh, digital realm, we'll have to consider it as, we'll have to make it finite somehow. So how do we do that? That one requires us to do all these things that I just said here. The reason we have to make it periodic, because otherwise we'll have infinite number of sinusoids. And also, why do we need to consider only 1024 points and make it duplicated in both directions? So all of these things are done only to make the digital computers work with uh, the discrete Fourier transform. The discrete Fourier transform requires us to do all these things. Okay, so this is that is the basic takeaway from here. Okay, and if you look at the example DFT composition figure 8.1, that is this figure. Yeah, 8.1. Yeah, if you look at this one, you'll see that there are different versions, different cosine waves based on the frequency. There can be uh, a cosine wave with 0 or not 0, 1, DC at 1. Then there can be a cosine wave with frequency 1. Then there can be a frequency wave of cosine wave with frequency 2. That means if you consider this to be the period, there are two oscillations in between. Here there is only one oscillation in between. Here there are three oscillations within this period. It's from 0 to 16. So this 16-point signal can hold different kinds of frequencies. Okay, so this is frequency 0 frequency, this is 1 frequency, this is 2 frequency, this is 3 frequency. So in this way you can have different versions of cosine wave within this 0 to 16 point. Notice that these are all from 0 to 16. Also in a similar way you can have different frequencies of sine waves within this 0 to 16 point. Okay, so now let me go back to this part. So it appears that a 16-point signal can be being decomposed into 18 sinusoids, each consisting of 16 points. Okay, so if you notice that figure, you'll see that there are in total 18 sinusoids from 1, 2, 3, 4, 5, 6, 7, 8, 9. And if you consider the sine waves, 1, 2, 3, 4, 5, 6, 7, 8, 9. 9 plus 9, 18. So there are total 18 sinusoids possible using these 16 points. Okay, and these are all just varying in terms of the frequency. Okay, now let me get back to this point. So in more formal terms, the 16-point signal must be viewed as a single period of an infinitely long periodic signal. Likewise, each of the 18 sinusoids represents a 16-point segment from an infinitely long sinusoid. And the thing is, if you notice, there is a particular relationship between the number of points and the number of sinusoids you can create from these points. The usual, this will become clear later on, but for now, just remember, if you are decomposing an n-point signal from time domain to the frequency domain, you can have n plus 2 sinusoids represent that n-point signal. Okay, so for every n-point signal, it could decompose into n plus 2 sinusoids, where n by 2 actually this will be clear later on, but for now just remember there are n by 2 plus 1 real ones and n by 2 plus 1 imaginary components. And that means n by 2 plus 1 cosines and n by 2 plus 1 sine. Okay, not cosine, sine. Okay, anyway, this will become clear later on. Now you don't need to focus on this part. Just remember that there are in total n plus 2 sinusoids that can be decomposed from a 16-point n-point signal. So in the later chapters, we'll see some properties of DFT that will seem very confusing if the signals are viewed as finite, but become obvious when the periodic nature is considered. So this is just a heads up why we consider every signal for DFT to be periodic. Why do we, if it is not periodic, we make it periodic by duplicating it in both directions. The reason we do so is because there are some properties which will seem very confusing if you do not consider it in this way. So this is what we need to remember for now. And okay, now we come to the notation and format of the real DFT. So the discrete Fourier transform changes an n-point input signal into two n by 2 plus 1 point output signals, just like I discussed just now, that an n-point signal can be decomposed into in total n plus 2 sinusoids, where n by 2 plus 1 will be cosines and n by 2 plus 1 will be sines. Okay, so there are two n by 2 plus 1 point output signals. So the output signal is the input signal is said to be in the time domain, and the output signal is in the frequency domain. Okay, so this 0 to n minus 1, so there are n points here. So this time domain signal can be made to go through the forward DFT to produce two n by 2 plus 1 point signals. So here are n by 2 plus 1 samples, and here are also n by 2 plus 1 samples. And this is the real part, and this is the imaginary part. When we go to the mathematics, this will become a bit more clearer why we are calling it as real and why imaginary. But for now, just remember that there are in total 2 parts, and each of them are of n by 2 plus 1 samples. Okay, and these represent the cosine wave amplitudes, and the imaginary parts represent the sine wave amplitudes. The term frequency domain is used to describe the amplitudes of the sine and cosine waves. Okay, that is a single time domain signal can have in the frequency domain, it will have only amplitudes in those positions where the sine and cosine waves will have a particular frequency. This will become clear when we talk about the mathematics of it. For now, just remember that a continuous time domain signal can be a single spike in the frequency domain. This is just a single spike in the frequency domain. Suppose its frequency is 2. Okay, suppose its frequency is 2. Suppose from 0 to 16. Let's consider the previous example. So suppose it is from 0 to 16, there are 2 oscillations. So in the frequency domain, what we will get after we make it go through the DFT, what we will get is just an amplitude in the frequency. So this is in the time domain, this is the time. So 0 seconds and this is 16 seconds. Within 16 seconds, we are getting 2 oscillations. So in the frequency domain, this axis is the frequency axis. Okay, this is not time, this is frequency. Here it is time, and this one is frequency. So here in one we will have 0, in all points we will have 0. We will only get one spike in the 2, frequency 2. So this is what is normally what we are supposed to get. So a time domain signal, if it is made to go through DFT, it will put in the frequency domain representation, we will get spikes in those, for those positions in those frequencies which are actually present in this signal. If there are multiple frequencies present in this signal, suppose this signal, this original signal was created using by summing 2 signals with different frequencies, then what we will get is, suppose it is something like this. So there are 2 frequencies here, it is sine, and at the same time there is also another frequency present here. So if it is something like this, then what we are going to get in the frequency domain representation are spikes in 2 different locations. Okay. And this is the ideal case where we get spikes like this. In reality, we do not get spikes like this, we get something like this, and here we will get another spike, something like this. There will be multiple points to represent a spike, not a single point. So anyway, we will see later on how this happens, but for now this is just to remember that from time domain to frequency domain, this is what we are supposed to see. Okay, so the frequency domain contains exactly the same information as the time domain, just in a different form. So as you can see, in the frequency domain, what we have are just spikes in the frequencies, in those particular frequencies that are present in the time domain. So both of them actually are representing the same thing. If you make a time domain signal go through DFT and you produce the frequency domain representation, there is also an inverse DFT that you can apply on the frequency domain representation to get back the time domain. So as you can see here, there is a forward DFT that takes you from this to the frequency domain. Also, there is an inverse DFT that takes you from the frequency domain to the time domain. Okay, if you know one domain, then you can calculate the other. And given the time domain signal, the process of calculating the frequency domain is called decomposition analysis, or the forward DFT, or simply the DFT. Okay, and the other way around, that is from frequency domain to time domain, it is known as inverse DFT, or in other words, synthesis. So it is called synthesis because here you are summing 2 signals, real component and imaginary component, to get one signal. And here it is called decomposition because here you are decomposing or dividing one signal into 2 components, real and imaginary. Okay, the number of samples in the time domain is usually represented by the variable n, and n can be any positive integer, but we usually choose n to be a power of 2. And the reason of it will become clear later on. There are actually 2 reasons. The first reason is mainly because because we are working with the signals in a digital system, and in digital systems the memory is designed in terms of powers of 2, right? Binary, we address everything by using binary addressing, and they're making the signals, storing them as powers of 2 is a natural signal length. Okay, this makes it easier for the digital systems to address them, and there is no leftover points. Okay, we do not have to truncate anything. So that is one of the reasons why we consider every endpoint signal to be where n is a power of 2, such as this 128, 256, 512, or 1024. And the other reason is that the most efficient algorithm for calculating DFT, that is the fast Fourier transform, usually operates with n that is a power of 2. So if we have time, we will also cover fast Fourier transform, even though I'm not sure whether I will be able to include it in the syllabus or not. But if we are able to cover it, then you will see that in fast Fourier transform, it goes through a kind of divide and conquer process. So if as you know, by a divide and conquer process, what would you need to do? You remember from algorithm that you can divide a problem, an n sample problem, into two n by 2 sample problems, and each of these n by 2 sample problems can be divided into n by 4 sample problems, right? And you can perform at the end you will have something uh, that will produce some elementary result, and that can be used by a recursion method that can be used to get back the higher topmost sub problems, and this can be used to get the overall the result for the overall problem. So anyway, this kind of uh, implementation of an algorithm requires the original point or original signal to be a power of 2, so that we can accurately divide it in this way. So that is the reason we also consider the value of n to be a power of 2. Okay, the standard DSP notation uses lowercase letters. This is just another thing coming out from the variable, and we are now discussing about another thing, that is the representation in terms of literature. So in literature, we will discuss about DSP notations in this way: X, Y, and Z. These small letters will represent the time domain representations of signals, and the corresponding uppercase letters, that is capital X, capital Y, capital Z, will be the frequency domain representation of these signals. And obviously the values in time domain and the values in frequency domain will be different, because just like I said, a time domain signal has the amplitudes like this. Okay, so it has amplitudes like this. So the values that you are storing are like this, but in the frequency domain, the corresponding values will be something like in one particular position you may have a spike, and in other positions you may have 0. Okay, so obviously this will be different. And for illustration, let us assume that an endpoint time domain signal is contained in here, small x. The corresponding frequency domain of the signal will be in the capital X, and this will consist of 2 parts. The capital X will consist of 2 parts, each an array of n by 2 plus 1 samples. And you already know where this is coming from. So the real part of X will have n by 2 plus 1 points. So small x has n points from 0 to n minus 1. There are n points. In the capital X, there will be 2 parts, rex. Okay, so this is rex, that is the array with the real part, and the imaginary part of X will be considered in an array imx, and this will also be of 0 to n by 2. From 0 to n by 2, there are total n by 2 plus 1 parts, and here also 0 to n by 2, there are total n by 2 plus 1 parts. So these will contain the values of the amplitudes of the cosine waves, and imx will contain the value of the amplitudes of the sine waves, and the summation of the cosine and sine waves will produce the original x. So this is the basic idea of decomposing an endpoint signal into 2 n by 2 plus 1 point signals. So, and another thing is that the horizontal axis of the frequency domain can be considered in 4 different ways. Okay, so in time domain, the horizontal axis always represented time, or basically the number of samples, in other words. Okay, in the time domain. But in frequency domain, this axis can be considered in different ways. Here we can actually, those are all the same representation, but we can put the values in different ways. Okay, so one way, in the first method, the horizontal axis is labeled from 0 to 64. So suppose this is a corresponding to the 0 to n by 2 plus n by 2 samples in the array. So in this case, the original samples were considered as n equals to 128. Suppose here there were 128 points in the time domain. There are 128 samples, or 128 seconds if you consider. In the corresponding frequency domain, what we will have is that the horizontal axis will have 65 points, n by 2 plus 1, right? So there will be 65 points, and these 65 points will be from 0 to 64. There are 65 points in total. So this is one way to represent the samples in the frequency domain. Okay, and there is also another way. So there is also another way, the second method. In this method, the horizontal axis is labeled as a fraction of the sampling rate. So instead of sample numbers, that is from 0 to 64, we can consider it as a fraction of the sampling rate. So this means that the values along the original horizontal axis will run from 0 to 0.5, and this one is actually coming from the sampling rate where I in chapter 1 of the other book, Proak's book, I actually discussed about this, that the unique frequencies only appear from 0 to half of the sampling frequency, and everything after that will just be repetitions. So the unique frequencies only appear from 0 to half. So here you can also represent it in this way, from 0 to, instead of 64, you can represent it using 0 to 0 to 0.5. Okay, and which of these frequencies you actually have in the time domain signal, only there you will have the amplitudes. Okay, so this is also another way of representing frequency domains, the axis of frequency domains, and you can see the examples here. There are some examples, each one showing different ways of representing. So this one is represented using the sample number from 0 to 64, and this one on the other hand is represented using this method, that is fraction of sampling rate. This one is a fraction of sampling rate from 0 to 0.5. Here there is no unit, and here also there is no unit because this is just a number, sample number. Okay, and the real and imaginary parts are written as where f takes on n by 2 plus 1. Yes, so we have already said all these things. Here the relationship between these two representations, that is from the sample numbers to the fraction of sampling rate, can be obtained in this way: f equals k by n. Okay, so this is just the way to convert from the first notation to the second notation. Here the first notation, the kth sample number. So if you are considering the kth sample number in this notation, where that point will be, so that will be found using f equals k by n. So the kth point in here will be that particular position. So suppose we are considering 32, so k equals 32. So k 32 divided by n is 128. So divide 32 by 128, you're going to get something like probably 0.25 or something like that. So this is the point. So if this is the point you're considering here, notice this sample here. So here it will be somewhere around here, right? 0.25. So this is the value that you're going to get if you divide 32 divided by 120. So this is how you can translate from one representation to another, from sample number to fraction of sampling rate, that is f. The third style, there is also another method of representing, but this is actually similar to the second. This is just representing in terms of radians. So here we were representing in as a fraction of the sampling rate in hertz. So here we are just representing in terms of radians. So this will simply be half of 2 pi, which will be just pi from 0 to pi. The axis will be from 0 to pi. So here the horizontal axis is just multiplied by 2 pi. If you multiply this by 2 pi, the last point will be equal to pi. This will be 0. So this is what you're supposed to get. The index in here will be labeled from is labeled using omega, and the value of omega can be from 0 to pi, as you can see here. And this one is called the natural frequency. So this is the natural frequency representation, and it has the unit of radians. This one is the frequency. I mean, this one is the hertz representation. Okay, we do not usually put hertz here as the frequency unit, because this is a fraction, and a fraction is always unitless, because we are dividing unit by unit. But here, since we are multiplying using 2 pi, which has a unit, so it has a unit, and the unit is radians. Okay. So the fourth, and there is also another method. The fourth method for representing the horizontal axis is by using the analog frequencies, and this one is just hertz. Here you just represent using hertz instead of giving this from 0 to 0.5 of the sampling rate. Here you just totally give the what will be the value of the sampling rate. That means here you just put the unit. So if the sampling rate is like 20 kilohertz, 0.5 of it will be 10 kilohertz, right? So the last point will be 10 kilohertz. First point will be 0 kilohertz. So if you put the actual values of the sampling rate and use it to populate the values in the horizontal axis, then this is actually the fourth method. And the reason this one is not used much is because this type of implementation is very specific to one particular application, and this is not general. So this is why we do not represent it normally in this way. but it has the advantage of presenting the frequency data in terms of a real world value. Okay, but just as I said, the disadvantage is that it is tied to a particular sampling rate. That means it is only applicable for one particular application where you have this sampling rate. For a different sampling rate, the values, that means the horizontal axis will be changed entirely. So usually we do not use it in DSP. Okay, now we come to the final topic of today. That is basis functions. The DFT basis functions are just a set of sine and cosine waves with unity amplitude. So the basic thing to remember is that what is a basis function here? A basis function is are those functions that you can use as fundamentals, as building blocks to produce any arbitrary signal. So any arbitrary signal can be represented using sums of these basis functions. And these basis functions are basically sines and cosine waves with unit amplitude. Okay, if you assign each amplitude to the proper sine or cosine wave, the result is a set of scaled sine and cosine waves that can be added to form the time domain signal. So just what I said right now. So yeah, each of these basis functions will be represented using this notation ck and sk. So there are two kinds of basis functions. One are the cos functions and other are the sine functions. They only differ by the frequency. It is 2 pi ki, and here k can determine the frequency. Changing the values of k, we can get the different frequencies of cos and sine, and by adding them we can get any signal. So these are known as the basis functions. And the very first basis function c0, if you put k equals to 0 here, the first function that we get is c0, which is this. It will have 1 and 1 and in all the positions, and the other one we have is s0, which will have 0 in all the positions if you put k equals 0 here. Okay, so for all the sample numbers we'll have 0. If you put k equals 2, so this is what you will get. Okay, you'll get 2 revolutions within this 2 vibrations within this n points. So here if n equals 32, yeah, so if you have n equals 32, you're supposed to get 2 points, 2 revolutions within these 32 points. And similarly for for sine as well, you're going to get 2 revolutions within this time frame, but you'll see that they're actually shifted versions of each other. The cosine and sine are actually just shifted versions of each other. Also for k equals to 10, this is what you're going to get. For k equals to 10, this is the sign that you're going to get. So these things only vary based on the value of k. So there you can have 16 unique k values for k within this 0 to 32. So in total 33 points there are. So there are within this 33 points you can have 16 unique frequencies of sines and cosines. Now if you look at several of these basis functions in detail, you'll see that there are some ways you can actually consider both of them to be same. If you consider this S16 and S0, if you look at them closely, you'll see that the points here and the points here are exactly the same. There is no way to actually differentiate between these two. The fact that the first one had no revolutions, no vibrations within these 0 to 32 points. It had no revolutions, and it produced these samples. And here also it had it had a lot of revolutions. It had exactly, I think, 16 revolutions within this 0 to 32 points, but still it produced the same sample points. Okay, so the thing is that these two are essentially the same. S16 and S0 are essentially the same, and this will be useful later on when we are talking about this in detail. And the first, but from the cosines perspective, this is different. In the cosine, for k equals to 0, we have all 1. That means a complete DC component. And for c equals 16, that is n by 2. Here we have alternations. This is the biggest frequency that we can get. Okay, so we have alternations, complete alternations for k equals 16. Okay, so if there are n samples entering the DFT, there are n plus 2 samples exiting. Where did the extra information come from? The answer is that 2 of the output samples contain no information. So you might be thinking, just from what I said before, for n samples, you're getting n by 2 plus 1 real components, n by 2 plus 1 imaginary components. If you add them together, you get total n plus 2 samples, not n. So where are the other two samples, extra samples coming from? So the reason these two extra samples are added, but still they do not uh, violate the law of superposition. That is, adding them will give you the original signal. But here you might think that you are not getting the original signal. You're getting two samples extra. So the reason that that does not actually violate is because two extra information that are coming, they do not uh, hamper the original signal, because two of the output samples contain no information, allowing the other n samples to be fully independent. So if you can see, there are 2 points that do not carry any information, I am x0 and I am x n by 2. In this case, if you relate it, then this is the first sign component 0, the 0th component, and the 16, I mean n by 2th component. This one has, these two are essentially the same. Okay, so these two do not hamper the original signal. So if you add them, these 2 points will not hamper the original signal. The other values are all unique, but these two are the same. S0 and S16 are the same, and they are all zeros. So in total, even though mathematically we have n plus 2 samples, but among them two frequencies are not producing any problem with our original signal. So that will be all about the theory of DFT. The rest of the next portion that comes here are basically the mathematics, the synthesis, that is calculating the forward DFT and the inverse DFT. Synthesis is the inverse DFT and decomposition is the forward DFT. We will be talking about that after our meet, or if I decide to continue some portion of post meet, then that will also be covered, but that won't be included in the final syllabus. For now, this is the theory part is all we need to worry about. So that will be the end of this lecture.